Hey everyone, in this problem we're given the description of an electron that is in a uniform electric field, and we're asked to find few things about the electron related to its energy after it has moved a distance of 3.20 centimeters. Now part A is specifically asking for the amount of work done on the electron by the field. Now this is simpler than it looks. All we have to do is use the basic work equation, which states that the amount of work done on something is equal to the magnitude of the force on that thing that is being done, times however far it has been displaced, which in this context is just going to be equal to the distance that we've been described, 3.20 centimeters. Now first off, for the force for this variable, we're not given the force exactly, but we do know that this is a force caused by an electric field, and we have a formula for that. The force due to an electric field is equal to the charge on the particle that is being moved times the magnitude of that field. So, I'm going to write that into this equation. Instead of F, I'm going to write it as QE, where Q is just going to be the charge of an electron, a negative charge, and E is the magnitude of the field that has been given to us. And then this is multiplied by the displacement we have. Now let's just fill out our numbers. For Q, that is a charge of negative 1.60 times 10 to the power of negative 19 coulombs. E is given to us 375 newtons per coulomb. And for delta X, this is where it might get a little bit tricky, because we can't just put it in 3.2 centimeters, at least not if we're going to consider the signs. Because the thing is, since this is an electron we're looking at, and because the electron has a negative charge, it is going to accelerate in the direction opposite to the field. And note that it says, the problem tells us that the field is pointing in the positive x direction, which means that the electron will be moving in the negative x direction. So its displacement should be written as negative. It's going to be negative 3.2 centimeters, which converting that into meters is 3.2 times 10 to the power of negative 2 meters. And so this negative sign cancels out with the other negative sign. So we're going to be left with a positive answer. So we put that into our calculator, and we find an amount of work of about 1.92 times 10 to the power of negative 18 joules. And that is the answer to part A. Now part B asks for the electron's change in potential energy due to this lovely little motion here. Now this is fairly simple because when we're dealing with electric potential energy, a change in potential energy is equal to the negative of the amount of work that has been done. So all we have to do is take the answer we just found, since that's the work, and make it negative. So our answer for this part is just negative 1.92 times 10 to the power of negative 18 joules. And that's the answer for part B. Now for part C. Part C asks for the electron's velocity. Now velocity is associated with kinetic energy, so you might think that this has nothing to do with the variables we worked with in the previous two parts of the problem. But here's the thing. The Coulomb force, like many forces, is considered a conservative force, which means that it, on its own, doesn't add energy to the system. So our total change in energy of the system is still zero, which means that if we were to sum up the changes in energy of the system, we would find, logically, that the change in kinetic energy plus the change in potential energy of the system is equal to zero. Because of the conservation of energy, the total energy stays the same. Which means that whatever change in kinetic energy there is, it's going to be equal to the negative of the change in potential energy because of this formula. And what that means, if that's the case, let me fix that. So what that means is that if kinetic energy is equal to the negative of the potential energy, well, we just found that our potential energy is a negative number, negative 1.92 times 10 to the power of negative 18 joules, which means our negatives will cancel out. So the change in kinetic energy is basically just the same thing as the amount of work we found in part A. It's just that positive number. That's the change in kinetic energy. So all we have to do is use our typical formula for kinetic energy. Kinetic energy is equal to 1/2 mv squared. 1/2 times the mass of the particle times the square of the speed. In this case, we're looking for that velocity. So we just have to solve this equation for v. So we can just do that algebraically. So multiply both sides of the equation by 2, divide both sides of the equation by m, and then take the square root of both sides. So that we can find that the velocity, or rather the speed, is equal to the square root of 2 times the change in kinetic energy. Oops, let me make that a little neater. Divided by m, which in this case is the mass of an electron. Now, to take care of this, we'll just plug in our values. So kinetic energy, so square root of 2 times the kinetic energy, which is the same value you've been working with all this time, 1.92 times 10 to the power of negative 18 joules, divided by the mass of an electron, which if you don't know, you can look up, and it's 9.11 times 10 to the power of negative 31 kilograms. And if you plug that into your calculator, then we find a value, we find a speed of 2.05 times 10 to the power of 6 meters per second. And that is the speed of the particle. The problem asks for the velocity, which means we have to incorporate direction as well, so that we're answering as a vector. And as we discussed earlier, the reason I made the displacement negative is because of the fact that the electron is going to accelerate in the direction pointing opposite to the electric field, which means that our velocity is going to be pointed in the negative x direction. And so that's how we can answer this as a vector. And that is it for that part of the problem, which means that is it for the entire problem. I hope this video helped you out. If it did, please consider subscribing, as that'll help me out in making more videos like this. I'm going to finish talking now because I think I have a hair in my mouth. Yes. If you have any questions, leave a comment down below. If you have a request for a future video, or you just like to hang out, my Discord server and my Twitch page are linked in the description below, so check those out if you'd like. But that's all for now, and I hope you all have a lovely night. Bye-bye.